All right, so here is schematics for a turbojet. So at the top, we have all the components, like a side view profile from A to the diffuser, which is at 1, to the compressor at 2, to the combustor at 3, to the turbine at 4, could have an afterburner between 5 and 6, to the nozzle at 6, and then the exit at 7. Down here I just made a block diagram showing the components. So you have the diffuser, the compressor, the combustor, the turbine. You could have the afterburner, and then the nozzle. Each one of these components has some sort of efficiency. Some have a adiabatic efficiency to be more realistic, where the combustor will have its own efficiency based on combustion process. Okay, so those are going to be ADAs. And then each one of these components could have its own gamma, so its own specific heat ratios. Furthermore, down here at the bottom left, you'll see RD, which is P naught over P naught A. Those are pressure ratios across the component. Okay, we also have PRC, which is the stagnation pressure ratio across the compressor. You have RB, P naught 4 over P naught 3, which is the pressure ratio over the combustor. The turbine RT, P naught 5 over P naught 4, and P naught 7 over P naught 6 for the nozzle. Okay. Now, some of these ratios for pressure, if I don't provide them, we're just going to assume 1. Okay. So again, schematic, each component can have a pressure ratio, has an efficiency, has different specific properties for air going through it. Okay. So here's the schematic, here's the block diagram, and let's go over here and say let's provide some values to these. Then I'll put properties of the air. So we're using air. We're going to assume 287 for R joules per kilogram K. And then each component will have its own gamma. We're going to assume the diffuser is 1.4, the compressor 1.37, the combustor 1.35, the turbine 1.33, and the nozzle 1.36. Okay, now these adiabatic efficiencies, the diffuser 0.97, the compressor 0.85, efficiency of the combustion process, we're going to just assume 1. RB, we're going to assume 1. A to T, 0.9 for the turbine, the nozzle 0.98. Okay, and then I can define RT as 1 and RN as 1, just for completeness. PRC, this is that critical pressure ratio for the compressor, okay, is 80. The fraction of fuel left over after combustion that's in the afterburner will be 1%. We're going to base this on 100 newtons of thrust. Atmospheric conditions or ambient pressure 18.75 kilopascals. The Mach number is 2. Ambient temperature 216.7 Kelvin. We have a heating value of 45,000 kilojoules per kilogram. And then we have the exit pressure is equal to the atmospheric pressure. Okay, and then over here, I'll just say find. We're going to find the propulsion efficiency, the thermal efficiency, and specific thrust. Now, if you remember, these are a function of F and UE, all of these. So you have to find the fuel to air ratio and the exit velocity. So to help, let's just make a kind of a outline. So at the inlet, what are we going to find? Well, we need to find T naught A. Okay. What about the compressor inlet? Well, we're going to assume T naught 2 is equal to T naught A, and we're going to find P naught 2 based on T naught 2. Okay. 3, at the outlet of the compressor, we're going to find T naught 3, which is based on T naught 2 and P naught 2. Okay. All right, what about 4? The combustor. Well, that's where we're going to find F. Okay. About 5, we got the turbine, or the turbine. P naught 4, let me do that in orange to keep it consistent. P naught 4, based on the pressure ratio. And we're also going to assume that the turbine power equals the compressor power. And what's that going to provide us? With T naught 5, which we'll be able to find P naught 5. Okay. Cool. And then finally, the nozzle. This is where we're going to find UE, and that's based on T naught 7 and P naught 7. And then T naught 7 is based on T naught 5 or T naught 6, which is, we'll assume, the afterburner, okay, parts. And then P naught 7 is based on P naught 5 or P naught 6, and we'll assume basically the afterburner or any other issues between the turbine and the nozzle. Okay. So if you look at this, we're going to go through each one: the inlet, compressor, inlet and outlet, combustor, the turbine, and the nozzle. And I'm going to show you all the equations we need and how they're formed to get F and UE. Now the last one I could put in here, I'll put right here, is the afterburner. And this is where we're going to calculate a new F at that point, called F2, and that'll be your overall F that you need to use, which is going to be your first F plus your second F. Okay? That is used in the efficiencies. Okay? So here is the general outline of what we're going to do to solve for F and UE, which are needed in the propulsion and the thermal efficiencies and specific thrust for this turbojet engine. Okay? All right, let's get started. Let's look at the inlet. Okay? So coming in the air, we can find T naught A by taking TA and multiplying it by this ratio, gamma D minus 1 over 2 m squared. And we've seen this, okay, multiple times. Stagnation equation, all right, isentropic, boom. All right, next one, compressor inlet. Okay, so coming in, I'm going to assume that T naught 2 is equal to T naught A. We have two equations that we're going to start with. We have equation 1, which is P naught 2 over P A equals T naught 2S over TA, okay, raised to the gamma D minus 1. Again, isentropic equations, all right, because it's at the end of the diffuser, all right. And again, we're including these S values, okay, because we're trying to get as close as we can to realistic. That's why it's T naught 2S. And the other equation we'll have, I'll put right here, equation 2. This is that efficiency equation that I talked about. H naught 2S minus HA over H naught 2 minus HA. Okay, so what we're going to do is plug in what H naught was, which is Cp of the diffuser, T naught 2S minus CPD of the diffuser, TA, remember H is equal to CPT, divided by CPD T naught 2 minus CPD of TA. And we can cancel all of these CPDs because they're the same. So we end up getting T naught 2S minus TA over T naught 2 minus TA. We're going to divide each term by TA on the right. So you end up getting T naught 2S over TA minus 1 divided by T naught 2 over TA minus 1. And then we're going to rearrange this for T naught 2S over TA because that is right here that we can plug in there. This becomes A to D, T naught 2 over TA plus, minus 1 plus 1. So again, take this equation, we're going to plug it into here, and we end up getting P naught 2 over PA equals, now this is a big equation, A to D, T naught 2 over TA minus 1 plus 1, and I'll erase this, gamma D over gamma D minus 1. All right. Cool. Next, the compressor. All right, compressor outlet. So we did the inlet. Let's look at what's going out the compressor. So compressor outlet. This PRC is P naught 3 over P naught 2. Okay, we pretty much are going to select this. All right. And then the other equation is our A to C, H naught 3S minus H naught 2, H naught 3 minus H naught 2. And we're going to do the same thing that we did before, Cp times T, but I'm going to skip some steps because it's the same kind of steps. And we're going to get T naught 3S over T naught 2 minus 1, T naught 3 over T naught 2 minus 1. Do some algebra, okay? And we're going to find T naught 3 over T naught 2, which is 1 over A to C, times T naught 3S over T naught 2 minus 1 plus 1. Okay, so I just rearranged that equation. What we need is, we had this equation defined. Okay, we also have to define the isentropic equation. So T naught 3S over T naught 2 equals P naught 3 over P naught 2 raised to the gamma C minus 1 over gamma C. So this, technically, we can plug in PRC raised to the gamma C minus 1 over gamma C, and then we can plug that into here. T naught 3 over T naught 2 equals 1 over A to C raised to the PRC gamma C minus 1 over gamma C minus 1 plus 1. Okay, which is basically, we're going to look for that F equation. Let's look at the conservation of energy, which is dE dt equals q dot net plus w dot net plus summation of m dot h plus v squared over 2 plus gz in minus summation of m dot h plus v squared over 2 plus gz out. Okay? So steady state, that's 0. In this, there is no mechanical work. So we get 0 equals the heat, including the efficiency of the burning of the combustor, is A to B times mass of the fluid times our QR, our heat value, plus 0 plus elevation changes, we'll neglect. And what's coming in is m dot of the air, h naught 3, and then we have minus m dot out times h naught 4. Okay? Or if you want, you could call this 3, doesn't matter, and this 4. Really doesn't matter right now, but we'll keep them consistent. Let's do 3 and 4. So what we end up having is m dot 4, h naught 4 equals A to B, m dot F, QR, plus m dot 3, h naught 3. Let's look at the conservation of mass. Summation of mass in equals mass out. Here we will, because of the mass of the fluid, include the fluid, mass of the air equals m dot out. But what I'll do is I'll change it to m dot 3 equals m dot 4. Okay, now let's plug in m dot 4 into the above equation. So we have m dot F plus m dot 3 h naught 4 equals A to B m dot F QR plus m dot 3 h naught 3. Again, define F as m dot F over m dot A, okay, or what do we call m dot A? M dot 3. So we're going to divide by m dot 3 in all of these terms. So we have over here, let's put, this is F plus 1, h naught 4 equals A to B times F times QR plus h naught 3. Now let's define like we did before, where Cp times T. So F plus 1 Cp T naught 4 equals A to B times F times QR plus Cp. This is T naught 3. And this is of the combustor. So we're going to put subscripts B on these CPs. And now we can solve for F, because that's used in the engine performances. So we get F equals T naught 4 over T naught 3 minus 1 divided by A to B QR over CPB T naught 3 minus T naught 4 over T naught 3. Okay, so you see T naught 3 is here. Okay, at the turbine inlet, we have P naught 4 equals P naught 3 times RB. Okay, so your burner stagnation pressure ratio, okay, which P naught 3 times P naught 4 over P naught 3. Okay, so depending on what this ratio is, you can account for some non-ideal cases. All right, let's move on. Okay, All right, so now let's look at the turbine. And what we need to assume at steady state that the work of the turbine should be equal to the work of the compressor. Okay, so if you did the energy balance of the turbine, you get m dot T, you'd get H4 minus H5, and then it would equal the turbine, m dot C, or the compressor, sorry, m dot C, H naught 3 minus H naught 2. So these two will equal each other. And these are found if you just analyze the compressor and did the energy balance on it. Now, if you change these, this could be m dot T of the turbine, and then this is CPT T naught 4 minus T naught 5 equals m dot C of, CP of the compressor. This would be T naught 3 minus T naught 2. Now, you can assume, and it's fine, that T naught 4 minus T naught 5 would equal T naught 3 minus T naught 2. We're assuming the mass flow rates and the CPs are pretty close, okay? M dot T CPT equals M dot C CPC. And that's okay. It's close, okay? What we need to do next is we need to find this ratio, P naught 5 over P naught 4, okay? So if we go all the way to the top, let's go all the way to our schematic. That is the change in pressure over the turbine, okay? Or the total stagnation pressure ratio, okay? Now, how do we find this? Well, so first equation is P naught 5 over P naught 4 equals T naught 5 S over T naught 4, isentropic equation. And this efficiency equation, H naught 4 minus H naught 5, H naught 4 minus H naught 5 S. And in this equation, you're going to do the same thing that we did before with those efficiencies. Plug in CP, T naught, and what you end up getting is this. T naught 5S over T naught 4 equals 1 over eta T, T naught 5 over T naught 4 minus 1 plus 1. Okay? Plug that into here, and we get P naught 5 over P naught 4 equals, bracket, 1 over eta T, T naught 5 over T naught 4 minus 1 plus 1 and bracket eta T over eta T minus 1. Okay, so we have that equation. Nozzle inlet. So T naught 6 equals T naught 5. P naught 6 equals P naught 5, and H naught 6 equals CP T naught 6. Okay. And then I'll go right here, the nozzle exit, T naught 7 equals T naught 6. Okay, and again, these are isentropic. There's no losses in these. P naught 7 equals P naught 6. H naught 7 equals H naught 6. Now, you can include, if you want, you can say P naught 7 equals Rn times P naught 6 if you want to include those non-ideal cases. Okay, so how do we find UE? Well, we need two sets of equations. We need TES over T naught 7 equals PE P naught 7 raised to the gamma n minus 1 over gamma n. Again, isentropic relationship. And if you remember the stagnation enthalpy equation, which states h naught equals h plus velocity squared over 2. We did this a long time ago. What we're going to do is we're going to call V UE, and these h naught and h are at 7. So it would be UE squared over 2 equals h naught 7 minus h7. Okay. Now, this we know from the efficiency equation is equal to a to n times h naught 7 minus h7s. Okay? Cool. Also note, h naught 7, CPN T naught 7, and this one is CPN T7s, which is really equal to CPN TES. Okay? 7 is your exit. And see this TES? That is right here. So TES equals T naught 7 times PE over P naught 7 raised to the gamma n minus 1 divided by gamma n. So we're going to plug this into that, into that, into this. Okay? So let's do this. So UE squared over 2 equals, and we're only going to look at like this term. Don't worry about that. Okay? That is going to be a to n times CPN T naught 7, which is this term. Okay? Then we're going to subtract CPN, and then it's TES, right? And I'll close it. But let's plug in what TES is right to there. So UE squared over 2 equals a to n CPN T naught 7 minus CPN, and then this becomes T naught 7 PE over P naught 7 raised to the gamma n minus 1 over gamma n. And this needs to be a bracket here, right? Because it's a to n all that times. Now, I can factor out a CPN and a T naught 7. So UE squared over 2 equals a to n CPN T naught 7 times 1 minus PE over P naught 7 raised to the gamma n minus 1 over gamma n. And also, I want you to know that CPN equals gamma n over gamma n minus 1 times R. How? Well, gamma n is CP over CV. We have R. At the bottom, we have gamma n, which is CP over CV, and then minus 1. Okay? This becomes CP times R over CP minus CV, which is CP times R, and this term is actually R. Okay? So what we're going to do is we're going to replace CPN with this term. Okay? And I'm going to multiply by 2. So you get UE squared equals 2 times a to n times gamma n over gamma n minus 1 times R times T naught 7. So 2. And then there's a bracket, 1 minus PE over P naught 7 raised to the gamma n minus 1 over gamma n, close bracket. And then you can take the square root to get UE. Okay, let's look at the afterburner. So, the afterburner we can do an energy balance. We're going to shoot extra fluid in there, fuel. Sorry, we're going to shoot extra fuel inside. We're going to call this m.f2, and we're going to use the same fuel so that it has the same like heating value. So this is your heat transfer of that. Then we have m.f plus h.f, and then it equals m.6 h.6. Okay, so pretty much coming into the afterburner and going out. Okay, now m.5 is conservation of mass. It's m dot of the air plus a fraction. We'll call m.f. Let's call this m.f times a fraction. Let's call capital F. So say 1% didn't get burnt from the combustor. Okay, and then this is m.a plus this fraction, okay, times F plus m.f2, okay. So it's the air leaving, it's a fraction of the fuel that wasn't burnt up, and this new fuel. Now we can rewrite this as m.f2 qr plus m.a plus, I'll call this just m.f for now, times h.5 equals, and I'll call this m.a plus m.capital F plus m.f2 times h.6. Okay, again, energy in, energy out. And we can divide every term by m.a, and we end up getting this. This would be F2 QR plus 1 plus F, I'll call F like a fraction, okay, H05 equals, this would be 1 plus the fraction F plus F2, okay, times H06, as you can solve for F2, okay. Just remember, there's this term and this term, okay. What you end up getting is 1 plus F the fraction times 1 plus H06 over H05 divided by QR divided by H05 minus H06 over H05. Okay. Or you can convert those to temperatures and CP values, right? So 1 plus F the fraction, 1 plus, this would be T06 over T05 because the CP's cancel. This would be QR. This is CP T05 minus T07, oh sorry, T06 over T05. And if you want, we can actually multiply this heating ratio by its burning efficiency, A to B, if you want to include that. Okay, so once you find this F2, okay, then you're going to, like the total F is going to be the F from previous plus F2, okay, which is then used in your engine performance equations, okay. And typically with an afterburner, your T06, okay, you're going to pick that. You usually pick it, okay. So before, without the afterburner, T06 was equal to T05. However, with an afterburner, you would pick, so you would pick T06 AB, your afterburner, okay. And H06 would be CP of your turbine, right, times T06. Okay, so I have provided you with information for the process of a turbojet from the inlet, diffuser, compressor, combustor, turbine, afterburner, nozzle to the exit. Step by step, we use isentropic equations, stagnation equations, conservation of energy, conservation of mass. Did a lot of algebra, and I hope it makes sense, the process of this turbojet engine. Okay, what we're trying to do is find the exit velocity, find the fuel ratios, and find the performance of these types of inlets so we can possibly change the size, change the shape, changes the pressure ratios, and try to get improvements to non-ideal cases. So that's why we have those adiabatic efficiencies, why we have pressure changes, stagnation pressures, because they deal with losses. All right, I hope you had fun listening and learning about turbojet engines. I'll see you in the next video.